All right, let's jump right in. Today, we're going to dive into the chemical world of cooperation. We're talking about covalent bonding. And it's this amazing story of how atoms figured out that sharing is, well, caring. This one idea creates everything from the water we drink to the hardest substance on Earth.
So, I want you to start with this question. What if atoms, just like people, had to cooperate to achieve stability, to survive, really? This isn't just some random thought experiment. It's the fundamental problem that countless nonmetal atoms are facing every single moment. They need something from their neighbors, but how do they get it?
You see, in the atomic world, there are kind of two ways to play the game. We've talked about ionic bonding before. That's basically the playground bully. It's the "I'll take your electron" approach, a total theft. But covalent bonding? It's different. It's a negotiation. It's two atoms looking at each other and deciding, hey, let's share. And that simple change in strategy, it changes everything.
Okay, so let's break this atomic sharing problem down. For an atom, the ultimate goal, the absolute peak of existence, is to be stable. And how do you get stable? You get a full outer shell of electrons, just like those super chill, super stable, noble gases. But here's the dilemma. Picture this. You've got two nonmetal atoms, say, two atoms of chlorine. Each one needs one more electron to be happy. But here's the thing. Neither of them is just going to give an electron away. No way. So, if stealing is off the table, what's the solution?
The solution is actually beautiful in its simplicity. The covalent bond. It's this strong connection where two nonmetal atoms solve their problem together. They do it by sharing one or more pairs of electrons. It's the perfect compromise, a total win-win.
So that's the why they share. But what about the how? How does this sharing actually work on a practical level? Let's get into the nitty-gritty and see how this leads to all sorts of different bonds.
It's actually a pretty straightforward process. Two atoms get close, they kind of cozy up to each other. Their outer electron shells start to overlap, and bam! They put a pair of electrons right into that shared space. And here's the magic trick. That shared pair now counts for both of them. It's like they both get to claim it, giving them both that amazing feeling of having a full, stable outer shell.
And get this, they don't have to stop at just one pair. Atoms can form single bonds, like in hydrogen. Or they can share two pairs, making a double bond, like in the oxygen we're breathing right now. Or, for the real heavy hitters, they can share a whopping 3 pairs, a triple bond. That's what you find in nitrogen gas, and let me tell you, that bond is insanely strong, which is why nitrogen is so stable in our atmosphere.
Now, trying to picture all this sharing can get a little complicated. So, chemists have come up with a few ways to draw it all out. You've got things like dot and cross diagrams to see where every electron came from. There are also displayed formulas, which use simple lines for bonds, super useful for bigger molecules. And of course, 3D models that give us our best guess of what these things really look like out in the world.
Okay, this next part is where things get really cool, in my opinion, because it turns out that this one simple idea, sharing electrons, can create two completely different types of materials. We're talking about the world of small, simple molecules on one side and the world of massive, giant structures on the other.
And this slide right here, this is the absolute key to understanding the whole thing. In simple molecules, like water, you have strong covalent bonds inside each molecule, but between one molecule and the next, the forces are super weak. But then you look at a giant structure like diamond, and it's just one continuous network of super strong covalent bonds, and that one difference changes everything.
So let's zoom in on those simple molecules. Remember those weak forces between them? We call them intramolecular forces, because they're so weak you don't need much energy at all to pull the molecules apart from each other. That's exactly why things like water and methane have low melting and boiling points. Oh, and they don't conduct electricity either, since there are no free charges floating around to carry a current.
But what about the other side of the coin, the giant structures? Just think about diamond. To get diamond to melt, you need to crank the temperature up to over 3,500 degrees Celsius. That is just insane. And why? Because you're not just overcoming weak forces anymore. Oh no, you have to physically break millions and millions of incredibly strong covalent bonds all at once. That takes a mind-boggling amount of energy. This leads us perfectly to the classic showdown, diamond versus graphite. I mean, think about it. They're both made of nothing but carbon atoms. And yet, one is the hardest natural substance known, and the other is so soft and slippery, we literally write with it. How on earth is that possible?
And the secret? It's right there in that first row. It's so simple, it's brilliant. In diamond, every single carbon atom bonds to 4 others, creating this perfect, rigid 3D lattice. It's locked in place. But in graphite, each carbon only bonds to 3 others. This forms these flat sheets, these layers of hexagons. And the forces between the layers are really weak, so they just slide right past each other. That's why your pencil works.
Okay, but wait a minute. That leaves one more mystery. If they're both just made of carbon and they don't have any ions, why in the world can graphite conduct electricity when diamond is a perfect insulator?
And the answer has a fantastic name, the delocalized electron. See, since each carbon in graphite only uses 3 of its outer electrons for bonding, that 4th one is kind of left over. It becomes delocalized, which just means it's free. It doesn't belong to any single atom, so it can just zip around between the layers. And an electron that can move is an electron that can carry an electrical current. It's the sea of mobile electrons that diamond just doesn't have.
So why does all this matter, really? Well, understanding these details is absolutely key, especially when it comes to busting some very common myths you hear all the time.
Let's do a quick pop quiz. It's a classic question. When you boil a kettle of water and that liquid water turns into steam, what is actually breaking?
Now, the number one mistake people make is saying that the strong covalent bonds inside the H2O molecules are breaking. But think about that for a second. If you were really splitting the hydrogen and oxygen atoms apart, you wouldn't be making steam. You'd be making a cloud of hydrogen and oxygen gas, which is, explosive. So that is definitely not it. The correct answer, and I really want you to lock this one in, is that only the weak intermolecular forces between the water molecules are breaking. The little H2O molecules themselves are perfectly fine. They stay completely intact. They're just moving much farther apart from their neighbors as they float off as a gas. And this really gets to the heart of it all. Everything we've talked about comes down to knowing which of these 2 forces you're dealing with. To melt diamond, you have to break the strong covalent bonds. But to boil water, you only need to overcome the much, much weaker intermolecular forces. If you get that one distinction, you've pretty much mastered this topic. At the end of the day, it's just incredible when you think about it. From the double bond in the oxygen that's filling our lungs right now, to the massive network of single bonds in a diamond, covalent bonding is the invisible architect of so much of our physical world.
This principle of sharing, it isn't just a chemistry concept. It's a fundamental building block of our reality. So the next time you drink a glass of water or write something with a pencil, just take a second and think, what else around me is held together by this simple, powerful act of sharing?